Here we're going to calculate the change in Gibbs free energy for a non-ideal liquid mixture. Given the mole fraction of component 1 is 0.3 in the liquid phase, and this mixture is in equilibrium with a vapor who has a mole fraction of 0.65 for component 1, and then the saturation pressures and the temperature and the total pressure are given. If we want to calculate the change in Gibbs free energy, delta G has two parts, and that's delta G if it were an ideal solution, and then the excess Gibbs free energy, we could write that as delta G excess, but normal G excess, and this is due to the fact that it's non-ideal. This is what accounts for that. And so delta G ideal solution divided by RT makes it dimensionless is just the mole fraction multiplied by the log of the mole fraction for component 1 and likewise for component 2. So let's calculate that, and I get a value of minus 0.611. This is dimensionless, and it's negative, as it should be for an ideal solution. The Gibbs free energy decreases when we create an ideal mixture. So likewise, the G excess term can be calculated. We're going to calculate G excess over RT to make it dimensionless, and it's x1 times log of gamma 1 plus x2 times the log of gamma 2, where gamma 1 and gamma 2 are the activity coefficients for components 1 and 2. And we're going to get those from the modified Raoult's law. So the modified Raoult's law is that x1 gamma 1 saturation pressure is y1 times p, and then the equivalent for component 2. So gamma 1, we have all the information, and so the value of gamma 1 greater than 1, and we're going to do the same calculation for gamma 2. And likewise, gamma 2 is also greater than 1. So now we can calculate the excess Gibbs free energy, and it's just substituting the values here. And so when we substitute in the values, take the logs, the activity coefficients, multiply by their mole fractions. Again, we get a dimensionless number. This value here is G excess over RT. So the total delta G, and again we'll write this as the dimensionless number, is the ideal solution plus the excess, and again both divided by RT. So I can substitute in the values I just calculated, minus 0.611 plus 0.521 equals minus 0.090, and it's negative, as it should be for a solution to form. The change in Gibbs free energy is negative. If I want the value of delta G, however, now I need to take minus 0.90 times R, and I'll pick units of joules per mole Kelvin for R, and times the temperature, 75 plus 273 to make this Kelvin, and I get delta G of minus 260 joules per mole.